So, dear friends, welcome to the first week for this program on 3D printing of exotic structures. Let us first understand what is the need of this particular program. In our country, despite numerous plans on paper, the manufacturing never took off in a meaningful way. The specific contribution of the manufacturing sector to the GDP is around 15%, and this data pre COVID, post COVID is almost on the same range. If we compare this with our neighbor like China, they are contributing more than 34% to the country's GDP from the manufacturing sector. The problem is not new, and the government of India is well aware about this problem. And to address this problem, in 2004, the government of India set up a National Manufacturing Competitive Council, which was basically managed by the group of ministers. And in 2006, the Prime Minister at that time, he also expressed his concern, and he also presented in front of NMCC that we must increase this contribution of the manufacturing sector from 12 to 14% to 25 to 35%. If we just see the Niti Aayog website, we'll come to know that government of India has set up a target of 25% by 2025, and still we are lacking behind. Not only the government is saying that we must increase this contribution, but other sectors like public sector people, private sector people, they are also in the same line. Like I have put one quote from the BHEL executive director. He is also on the same line that we must increase this contribution of the manufacturing sector. But it is not happening. What is the reason that it is not happening? There are some problems like labor laws, land acquisition, different type of bills. Because of our democratic structure, it is not easy to implement all these things in a single go, which is relatively in a different way in our country, neighboring country, that is China. Now, what does this mean? Whether we should stop working or we can have some innovative idea. So, in one of the discussion between CII and government of Andhra, they came up with a very innovative solution that innovation in product and process should be the key driver for the growth in the manufacturing sector. Now, this is the key point around which this whole story moves. That is the innovation in product or the process. I will just want to give one example on this. Like in our country, a lot of people move from one place to another place for the religious tourism, which is not the case in the western world, right? So whenever you go to some religious place, you want to buy some souvenir for your near and dear one. And whenever you go to any of the shopping place or market, some religious place, what we observe that people say, specifically if it is electronic related product, this is made in China, so whenever you will go outside the shop, this will having a no guarantee. Even then we buy. I personally have my own experience. I visited to one of the religious place in Maharashtra, that is Nanded, and I purchased one souvenir, uh, which was basically having a set of LEDs. And the shopkeeper told me that this is just 50 rupees. When you will go out, this will have no guarantee. But even then I purchased it. Now, what are the motivation? Point number one is cost. The second thing is the value addition. That is actually the thing that basically attract the customer for that. So what they have done on the same souvenir, they put a religious symbol and they put one quotation like Yatra Shri Hajur Sahib. So what I want to say from this is, by adding value into the product, by innovation, you can basically increase the sale potential. Just imagine 5,000 people visiting particular holy place, and more than 10% people definitely will buy. So what is a huge sale volume? So they did the innovation. So what is the innovation? Innovation is in the form of the product, right? So what we have to do is, even for our daily use product, we have to innovate. So that is what our PM was also saying. We have to be vocal for local. Even for our daily domestic products, we are not manufacturing, and that is being imported from the western world. So what we can do is, we can increase the contribution of the manufacturing sector in a big way. And it is projected that if there is a 10% increase up to 25%, it will have 100 million job for our countrymen. And this course that we are going for, the 3D printing part, this can actually help in shortening the product development cycle. This is one more title slide that I just want to present in front of you. This is the Indian perspective, that is by the Thomson Reuters. which is now overtaken by the Clarivate Analytics. What does this says? That Indian contribution in research was around 4.3% in 80s, and this was reduced to 2.2, 2.3% in 1995. Then in 2010 or so, it increased up to 4.25%, and presently still we are around 5% contributing. That means for 95% of the research in our country, we are dependent upon the Western world. But if we compare it with other countries like China, Korea, Taiwan, they are doing much better than us. We are normally saying that we are really good in computer science, but as per the third party data, we are just contributing around 2.5% for the international world. So basically, the idea is, but we have to innovate, we have to develop the product fast, and we have to really, come up with a product which is having a shorter life cycle, but this is first launched in the market. So this is the motivation for developing the new product. If you launch first, you will have a lion's share in the market, and for that, 3D printing is one of the route. In front of your screen, I am putting one classification that is based on the Chang and Chua paper 2005, Journal of Advanced Manufacturing Technology. What does this says? That rapid prototyping, rapid manufacturing can be basically subdivided into three categories. One is additive type, another is subtractive type, and then there is a combination of additive and subtractive. When you see the subtractive type, like using the CNC machine, we are quite familiar. Since 80s in our country, we are doing this in a big way. And once it is additive type, there are liquid based, powder based, sheet based technologies, and under that 500 plus technologies are available. Here the idea is not just to tell about the technology. You use powder based, you use metal based, you use different laser based processing, something like that, but how we can hybridize these technologies and can use it for actual application that is required at my place of work, right? Then people have reported the combination of additive and subtractive together also, right? The basic idea of this course will be of making these technologies in-house, adaptable to my local system. So that is the main idea of discussion. Now for the beginners who are just new to this 3D printing or additive manufacturing, it is just, I have a CAD data, you can see as it is projected in front of you in the form of a sketch. I have some data in the form of CAD file, and that CAD file is fetched to the printer, which just looks like a photocopier, and it is printing the part in the 3D form. So I am getting a 3D printed object, right? So the another way of explaining the same thing, let us say I am interested in some spherical job that is in front of you, and it is prepared in the form of different layers, and these layers were attached together, and I am getting a final product. Now attachment of one layer to the another layer may be through some adhesive, it may be through laser processing, it may be through partial melting, and the different ways using sintering and all, and idea is to join the part layer by layer. So each layer is attached to the next layer. There can be different way or different methodologies to join these type of layers, and this leads to the final development of the 3D printed part. Now what actually is the Oxatic for which this specific course is designed? That is the 4D part. Now to understand the 4D, I give a very simple example of a sunflower. It has very beautiful thing. Whenever there is a sunrise, the sunflower faces up, and once there is a sunset, it faces down. And as there is a movement of earth around the sun, we observe the angular movement left right over with the movement of the earth around the sun. There is some angular movement seen in the flower itself. So this means that there is some stimulus which is in the form of sunlight, which basically control up down left right movement. Now we want to use this for 4D part, right? Just imagine I have printed some part and I can give some stimulus to it, and with that stimulus it can change its up down left right movement. Now to give a simple example, in the mechanical application point of view, we are using a dynamometer for the measurement of the forces. Now how these dynamometer function? They may be strain gauge based or they may be piezo based. So in a typical piezo based dynamometer, if I apply a load, there is a change in the length. I release a load, it will come back to the original position. If I apply a load, release a load, again apply n number of times, I will getting a same change in the length. Now this concept is actually used for the measurement of the forces acting on the dynamometer, right? Now just imagine if I print that piezo based material 3D and then apply a load, it will have a 4D behavior. This is one way of getting the 4D behavior, right? So we call it as 4D is an extension of 3D through which I can give some stimulus, like in this particular example it was a load or the force applicable, which is giving me some 4D behavior. Now printing of smart material, is a 4D, right? Now to get a 4D, I can think of in a way like the smart material, it may have the intrinsic property or the extrinsic property. Like taking the same example of the piezo based material, applying a load, changing its length, releasing a load, coming back to the original length, this is the intrinsic property, internal property. So we normally see self expansion, self contraction type things, but sometimes these type of properties are not in the material itself. So what we have to do is we have to add the property from outside. So we call it as the extrinsic property, right? So for getting the extrinsic property, there can be two ways. One is the reinforcement and another is the metamaterial. Reinforcement, like for example, in case of the polymer, they are insulator and I want to make them conductor. So what I have to do is I have to add some property into it by reinforcing. Like I want to make them conductor, I can think of adding some copper particles, adding some graphene particles, which actually make it conducting, right? So that is one way of adding the property. The another important thing, that is the metamaterial, which is basically the auxetic structure, right? So adding the auxetic structure through metamaterial, this can be another way of getting the 4D part. To understand this in a simple example, we see the railway bridge, and in the railway bridge we have a trusses type link. So in those trusses we have a length of link and the angle of link, which is important to give me same modulus of toughness, which will be given by the solid structure. So basically I can reduce the weight of the structure parallelly, and I can basically reduce the cost also, right? So that is the one typical example of putting a auxetic structure or in the form of metamaterial to get a smart behavior. So this particular course that we are going to study will be applicable, will be useful when I will be using different type of metastructure to have some tunable property. So that is the beauty of the program. And I can even think of the programming of this type of structures. Like in the first example that we are seeing, let us say my material is in state A. I give some stimulus to it. So it goes to the state B. The stimulus can be temperature, the stimulus can be light, the stimulus can be some chemical energy, it can be humidity or electric energy, it can be magnetic field, it goes to the state B. Then you give another stimulus, it goes to the state A. So this is called one-way programming. The another way of programming is, I have material in state A, I give some stimulus on, it goes to the state B. You switch on the stimulus, it goes to the B. You switch off the stimulus, it come back to the A. One typical example is the use of the electric field or the magnetic field. Like for example, if I am adding some magnetic field in some area, so if I switch on the current, there is a increase in the magnetic field. You switch off, it will come back to the original position. Like for example, in our room, there is a ceiling fan and I have a regulator with me, and I can put that knob at different position, which basically adds the different value of resistance to the circuit, and I can control the RPM of the motor. So this is basically a two-way programming in which by adding or removing some resistance, I can basically control the RPM. So we call it as a two-way programming. Then there is a multi-stage programming, like material is in stage A, I give some stimulus, it goes to A1, you give another stimulus, it go to A2, and there can be multiple stages. At the end, the loop should be closed. So we call it as a multi-stage programming. So in this way, we can basically make the shape memory programming. Now I'm going to take you to the one basic 3D printing process, which will be helping us to understand how these material works and how to add value to these material that we will see in our different sessions. Now you see, as in front of your screen, this is one of the most commonly used 3D printing process. I believe in all polytechnic colleges, all engineering colleges, this type of setup is available. We call it as a fused filament fabrication. As per the recent ASTM code, it is also called the material extrusion process. Now, how actually it works? You see, there is a one spool of polymer which is right now, let us say, in dark blue color. So this is being forced to move into some area, right? Basically, where I have a arrangement for heating. You can see there is a liquefier zone. Basically, here I am having a heater, and it is being heating the polymer wire that is entering into it, and there are some mechanical drives you can see over here. Most of the commercial FDM based printer, they use this type of filament at the dia of 1.75, but commercially it is available from 0.4 to 4.0 mm, but one of the most commonly used size is 1.75 across the world. And if you buy these type of spool materials, this will be available in 1 kg, 2 kg, 4 kg, like that, and it may vary depending upon the polymer I use, and the cost may be in open market from 1500 rupees per kg to maybe 50,000 rupees per kg. Basically, what type of polymer I am using, what is its melting temperature, how properties I am adding to it, that is really important, which basically adds the cost. So the process is quite simple. So I have a filament over here which is in the form of spool. I am calling it as a build material. So this is being fed to this chamber, as you can see, and there are mechanical drives. Now at this case, here at this location, there is a nozzle attached over here. So commercially, the different dia nozzles are available, which are as of low cost, as cheap as 10 rupees to 20 rupees, 30 rupees. So depending upon the dia my requirement, I can think of 0.1, 0.2, 0.4, whatever I select. So accordingly, the nozzle can be there. Normally the brass nozzles are used, and what I am doing is I am feeding the filament over here and then pushing the filament through this nozzle, and the fine wire in the strand form that is coming out of the other part of the nozzle. Now that is being deposited layer by layer. For most of the commercial printer, the temperature that is put over here is in the range of 150 to 300 degrees Celsius. Even for the high end polymer printers, people are working like for the peak material that is called polyether ketone, that is used for the printing of vertebras. I am requiring the temperature to the range of 450 and plus, but that is a very specific requirement. But most of the commercial printer, they are in the range of 150 to 300. So again, the filament fed to this zone through some mechanical drive. It has a typical rollers putting into the liquefier zone, then pushing these material through the nozzle, very fine filament coming, and I am putting it layer by layer, and I am getting a 3D printed part. Now some of us may have a question, why there are two different color filaments over here. As you can see, the material that is coming out from this, we also call it as the extrudate, that is let us say in the temperature range of 250 to 300 degrees Celsius. So I need a sport to build this part. So what we use is we put another color filament over here, which is basically called a sport material, which is little like a green color in this case. That is actually the sporting this part. You see, this is like a cantilever. So if I have to sport it while printing, so I need another material that can actually sport the extended part like a cantilever. So that is the reason that the another sport material spool is being used. Now most of the sport material, these are water soluble, and the build material, these are non water soluble. So what we do is, after my printing is over, I put it into one ultrasonic chamber, in which this build and sport material part is put into that chamber. I give some ultrasonic vibration, 20-30 kilohertz, in a water solution normally kept at 65 to 70 degrees Celsius temperature, and the whole sport material actually dissolved in that, and finally what I am getting a final 3D printed part, right? So this technology is so easily available and the starting cost may vary from around 5,000. Even some models are available. But for the high end model, the beauty is to control the heat transfer rate. So people have the chamber outside this, which basically control the heat transfer rate. And finally, I'm getting a better dimensional stability, better accuracy, and of course, the surface finish, etc., is also controlled. Now, I'm going to show you one typical application in which we have basically prepared one of the filament in-house that can be used for these type of low-cost printers. And this is in line with, of course, the sustainable development goals. In this case, the recycled ABS and PS6 has been reinforced with the banana fiber. So ABS, as you know, is one of the highly used thermoplastic. This is acrylonitrile butadiene styrene, and PS6 is polyamide 6. This is basically a nylon, and 6 is the grade which is basically extrudable, right? So it has been reinforced with the banana fiber, and we want to enhance the thermal, mechanical, and the morphological properties for this. I would directly take you to the, one of the recent paper. There is a paper by Bahrain et al, in which he explained that how to condition those banana fibers. In a place like Jalgaon, there is a lot of agriculture waste in the form of banana fiber, and it is really voluminous, right? So what we can do is we can condition those banana fibers. There is a very extended study by Bahrain et al, and he explained that how to condition those banana fibers, and taking help of that study, we prepared the banana fibers of a particular length and dia, and we try to reinforce by weight into the ABS and polyamide 6. At the start, actually, we were not knowing what quantity I should reinforce into the my basic polymer, so that I can enhance the output in terms of mechanical, morphological, and thermal behavior. So we started just with a 5%, and we put it into the ABS as well as in the polyamide 6. Now this is the setup that you can see. This is a twin screw extruder. This is a thermo-based twin screw extruder. It has basically two intermeshing screws, and I put the material from here. I have the control like temperature. I have control like nozzle dia and the torque, basically the RPM. So based upon that, the filament is prepared, and that filament is fed to the printer. And as per the ASTM D638 Type 4, the samples were prepared. All the dimensions of the ASTM D638 are already standardized, and we put it on a UTM, and we try to fracture those samples and try to see what is happening at the fractured site. Now this is really wonderful and typical application to understand why and what will be the benefit of adding these type of reinforcement into the polymer. This is basically a DSC analysis. To understand the importance of this, I give you one simple example. Suppose I go to market and purchase two buckets of the same company, same color, same dimension, and one bucket I put in my bathroom and another bucket I have put on my rooftop. Now, what we will observe, the bucket that is in the controlled environment, that I see in my bathroom, it may not crack for 2 years or more, whereas the bucket that has been put on the rooftop may develop crack after few days. The basic reason is the change in the heating cooling cycle. In the morning time, let us say there is a excessive sunlight and heat is there, so it is basically absorbing the energy, and then in the night time, let us say the temperature dips and the there is a release, right? So if the energy absorbed and release is not in a appreciable range, applicable range, there will be a crack propagation. You must appreciate one thing. Let us say I'm using this type of polymer on the dashboard of the car or even on the bumper. What will happen if the energy absorbed and released is not in a particular range? There will be bulging in and bulging out type situation. Like for example, in my all cars, I'm using a ABS dashboard, right? And there is a high temperature outside. Let us say you go to some place in Rajasthan like Churu, where the outside temperature is 55 and the cabin is closed and there is no one in the cabin. The temperature inside cabin may go up to 70. So whenever you have to enter into the cabin, basically what you do is you start your AC. So because of the temperature condition that you want to maintain, let us say to 20 degree or 30 degree in a minimum time, the polymer must have a balance of the heating and cooling rate. Now the same vehicle now going to the Siachen glacier, the outside temperature -20, -30, -10, right? And basically you switch on your heater, right? Now again the heating cooling cycle must be in a appropriate range so that the energy absorbed and energy released is balanced. Now this is being judged through this. You see in this curve, along the x-axis I have two scales. One is the time scale, in which let us say 0, 5, 10, 15, 20, 25, this is for 85 minutes my process is running. And then on the upper scale you can see from room temperature to 250 I am heating, then from 250 to again room temperature basically I am cooling, then again heating up to 250, then again cooling, right? And on the y-axis basically I am measuring the enthalpy, what is the energy absorbed in heating and energy absorbed in cooling. So I am interested in glass transition of that material, I am interested in Tm melting of that material, I am interested in its nullity value and the enthalpy value. If it is same in the repetitive cycle, my material can be considered as a stable. If it is varying in heating cooling cycle, then some special treatment is required. So what we observed in this particular example, when we were using ABS with the reinforcement of banana fiber up to 5%, the temperature increased, like in this case from 190 to 212, and in the repeated cycle this was almost stable. Of course the single material was also stable, but with reinforcement the temperature was increased. That means my material can withstand the higher temperature. Similar observation was for the polyamide, and we try to observe some of the mechanical properties like in the form of peak load, break load. After you can see in this graphical representation, after every processing the mechanical properties were improved in terms of the load, in terms of the tensile strength. Similarly the elongation behavior was also improved. So we try to ascertain why this is happening. So what we observed is there is a basically the controlled porosity level that has been observed by using this type of reinforcement. It was really controlled, and which basically improved all the mechanical properties. And then using any optimization tool, one can basically think of what should be the porosity level, what should be the peak load, what should be the Young modulus, how to customize the MOT, so that can be managed and controlled with this type of optimization tool, right? So taking all this thing, let me take you to the another example. This will be a case in which the recycled polymer can be actually used for the polymer printing. Through polymer printing I am making it a useful product. For the basic understanding, just an overview, I need a setup which we call it as the MFI setup, which is basically a melt flow index. But I am interested in how much gram of material is flowing in 10 minutes. If larger quantity is flowing in 10 minutes, basically it is highly flowable and it can make the thin sheets, or it can go to the interstitial sites. And if MFI is less, basically I will not be able to make the thin sections. So whenever I am using a recycled polymer for my 3D printing, we have to first ascertain the MFI, and there is a special code ASTM 1238D. We will see specifically whenever we will talk about in our coming lectures, and how to optimize this. That will be the part that will be coming in the future. So what we have done in this case is we take example of a dry cell. You see in our dry cell there are 4 zones. One is having a graphite, another is having MnO2, then zinc chloride, ammonium chloride and zinc plate. So when I assemble all these 4 sections, the chemical energy basically converts into the electrical energy, and I am getting a output in the form of 1 volt, 1.5 volt, 2.5 volts, 3 volts, depending upon the surface area. I basically plan for these type of disk. What we observed that the part like zinc chloride, ammonium chloride, which is an electrolyte, that is consumed, whereas rest of the parts are not consumed in our dry cell. So what we try to do is we reinforce these different salts into the polymer, and try to make the polymer in such a way that that particular disc which is consumable, that is only replaced in place of replacing the whole cell. So this is basically again in line with the sustainable development goal of United Nations. So for that purpose, I need to understand what is the rheology, that is the MFI. So as you can see in this table, initially selecting 100% ABS, I am getting a MFI of 9 gram per 10 minute. Once I am adding the 10%, 20%, 30%, 40% graphite into it, or zinc chloride, ammonium chloride into it, or MnO into it, I am getting a different value of the MFI. Now what I want for my setup, this should be in a particular range, and the whole disk almost have a near about similar composition. Anyway, whatever is consuming at the faster rate, I will basically replace that disk and again reassemble it. You can see this is actual live 3D printing going on, and the assembly is there for these type of the product. So once we assemble all this and we attach the copper wire into it, uh, we were expected to have some output voltage, but to our surprise we were not getting any output. So we were really worried about what happened. This should be there as per the basic idea of the cell construction, dry cell construction is concerned. So what we did at that time, we put some drops of acetone at the interface, and once we did that, immediately we got a voltage of 1.5 volt. So we were really happy. So what we understood, that because of the interface of different polymeric material and the different salt, I need to excite initially for the jumping of the electrons to cross that barrier. Accordingly, we try to make some mechanical parts and check their mechanical properties. And one beautiful thing that we learned from this is, this type of cell that we have prepared right now is stable up to 95 degrees Celsius temperature. Otherwise, our normal dry cell, they don't work above 55. And similarly, on the lower temperature range, below zero, normally my dry cell don't work. Because these were giving the good output even up to -15, -10, really good output. So in low temperature areas, this can be really helpful. So this is the beauty of 3D printing, that we can use even daily use product for fabrication route through 3D printing, and can make them really customizable. We can customize the properties, and we can prepare them in-house. So this is the just the overview about the introduction, and in the coming session we will see some of the videos and actual fabricating part for these type of components. I hope you enjoyed this. Keep watching the next part. Thank you very much.